You stand right where I'm standing. You don't have to cut anything.
Can I see? Can I see?
Hmm?
Oh, that's the one.
There we go. Okay, it's working. You can hear us. So you are good to go.
Enjoy. Will you switch up the light? So I will introduce you. Yeah. Sorry.
There we go. Keep going.
So can I start?
Now you can start.
Okay, good afternoon, everybody. It's my great pleasure to introduce today's Geotalks presenters, Jörg and Renee. So Jörg did his undergraduate and PhD studies at the ETH in Zurich, working on metamorphism and tectonics of the European Alps before he moved to the Research School of Earth Sciences in Canberra, where he worked on metamorphism as well. Since 2015, Jörg is full professor in Bern, and his main research focuses on subduction zone processes using a combination of experimental petrology, trace metal geochemistry, and various other techniques. And our second presenter is Renee. Renee is currently a postdoc in Bern as well. She did her PhD in Adelaide, and subsequently she went to Bern, and the way she's a petrologist working on subduction metamorphism, metamorphic rocks, crustal formation, and the geochronology of minerals. So today they will give us, in the next 45 minutes, new insights into subduction processes and the fundamental link between chromatiates and TPGs.
Thanks very much, Robert. It's a great pleasure to be here, and thanks for the hospitality. This is much appreciated. So what we want to do is that in the first half of the talk, I will talk about the modern Earth and how water recycling is achieved to that. That is in collaboration here with a series of collaborators, postdocs, as well as PhD students. And in a nutshell, what we want to find out is how we get from this here, so in a kitchen analogy, that is a serpentinite, salt and pepper, to a granite benchtop. So how the link is between these two very different rock types. And that has all to do with the deep water cycle. So let's have a look at the deep water cycle. There are three different cycles. That is where we can water uptake through to weathering and recycle within the crust. We can have a much larger cycle where we have water uptake in oceanic settings, where we have alteration of oceanic crust, and then we have recycling here through subduction zones. And then there is even a larger cycle, and that is water that is retained in the slab and can travel all the way down to the core mantle boundary to be recycled along mid-ocean ridges again. And we see that the timescales of this recycling is vastly different. It is about 0.1 to 10 million years, 1 to 10 million years for the subduction recycling, whereas for the deep water cycling, this is in the order of 100 to 1,000 million years. And the question, of course, is, and that is still an open question, that we don't know if this water cycle is actually in a secular equilibrium or not. A thing that we can discuss. If you want to get a first order constraints on volumes or of how this efficiency of recycling is quite instructive to look at inputs and outputs. So when we look, for example, at volcanic arcs, we produce 5 cubic kilometers per year with 4 weight % of H2O. At mid-ocean ridge, we have about 4 times higher production of material, 20 cubic kilometers per year, but with much lower water contents. So from this, it seems that we have about 10 times more water recycling through subduction zones than we have through the deep Earth's deep mantle recycling, and then coming up the mid-ocean ridges. And if you want to have an estimate, a conservative estimate on how much we have in a depleted mantle, the source of the MORPs, then we have at least 100 ppm of water that has to be retained and has to be replenished through subduction. So, as I said, the subduction recycling versus the deep mantle recycling, what is happening here is not well constrained. But the talk today will mainly focus on these first three arrows, what happens here from the oceanic plate hydration to subduction and how we can constrain these recycling. So why are we interested in that? Then several reasons why water is absolutely fundamental for understanding the Earth as it is, as it functions today. As H2O has influence on many properties like density of the rocks. We have the melting behavior, of course, but also seismic wave speed, electric conductivity, magma differentiation, rheology, diffusion properties, all depend on the presence or absence of H2O. Now, the approach, how can we get into this very deep region here to understand what is happening in subduction zones? There are several different approaches that we can do. We can have a look at rocks that are exhumed from subduction zones and do field work. We do then the petrography and petrology. Then we need to couple that with experimental methods where we can reproduce the conditions in subduction zone conditions. And then we need to have advanced analytical techniques to investigate the experimental products as well as the natural rocks. So let's start at the start, serpentinization, water uptake. That happens in mid-ocean ridge settings, and I will focus in this talk mainly on the ultramafic rocks. And that is because these are the rocks that have the greatest capacity to actually incorporate water. When we serpentinize a mantle rock, we have magnesium iron olivine reacted with H2O, and then we form serpentine minerals, and we can form a little bit of brucite, and then we have a very interesting reaction going on, and that is that the iron 2+ that we have in the olivine will be oxidized partly to form magnetite that is having iron 3+. And in this reaction, we have the liberation of H2. And this is really a very important reaction, because if we then go very back in Earth, and also when we go to the white smokers, for example, in the Atlantis Massif in the Atlantic, we see that this is a very cheap source of energy where microbes can feed on. And this could well be that among the earliest life forms were harvesting this type of energy in order to evolve and to thrive. Just a reminder, serpentine is a very hydrated mineral, has about 12% of water, and that is the reason why we focus on this mineral. So where do we have serpentinization? There are three main regions where this can happen, and that is the first one, obvious one, is at mid-ocean ridges. And here we need to distinguish between slow and fast spreading ridges. The slow spreading ridges have much more capacity, possibility to be hydrated. Then the depth of alteration is of course important, and especially when we have oceanic core complexes or when we have fracture zones. That is the way how we can drag water into the mantle and then serpentinize the rocks. Then another one is when our oceanic plate is entering the subduction zone. As you can think, when it is bending, there is cracking, is deformation going on, and because I've shown that here we have the possibility of serpentinization at great depths in the incoming subducting plate. But the extent of serpentinization here is still one of the big unknowns, and is probably one of the biggest unknown in the deep water cycle. And then the third place where we can have water uptake is when we serpentinize the mantle wedge, when we have fluids coming off from green schists and blue schists of the subducted oceanic crust, and they infiltrate the mantle wedge, and then they can serpentinize the hanging wall of the subducting plates. And in such a setting, we can have also very chloride-rich schists in melange zones, and the role they might play, we will see a little bit later on. So now we have a hydrated rock, and now we want to find out what is happening when do these rocks dehydrate? It is quite important then to see where the water is liberated. And this is actually quite a complex problem. As we can see, it depends mainly on two main things, and that is, on one is the temperature structure in subduction zones, and the other is then the thermal stability or the pressure temperature stability of the hydrous phases in the subductive plates. And each of these two main things, they have quite a difference. They have a variation. That is, for example, the age of the plate, the speed of the plate, how the plate boundary behaves, if you have friction, if you have coupling, if you have decoupling, the mantle wedge temperature, strong gradients within the plate. And if we do that, it's actually quite amazing that the different models for the temperature structure in subduction zones, they can differ for a given depth by several hundreds of degrees, just by varying these parameters. On the other hand, if we have such a slab geotherm, as shown here in the light blue, as a selection of geotherms, then we need to intersect them with the dehydration reaction of our hydrous phases. And that is, of course, dependent on the composition of the rocks. And quite often there is a difference between experimental results on one hand and what comes from natural rocks on the other hand. So now let's go a bit into the field and have a look at a nice subduction zone where we can look at subducted rocks. We see here beautiful pillow lavas, well-preserved pillow lavas. And if we zoom in, we see that they consist here of garnet and anthracite. So these are clearly aquagite facies pillows. They haven't been deformed. They have been subducted to 80 kilometers depth and have come back nearly intact. So this is in the Alps. That's the Zermatt, the Matterhorn, iconic mountain. And here in front, we see some of these relics of subducted oceanic crust that is now sandwiched between Africa and Europe. So that was the ocean that once separated Africa from Europe. So the aquagites are a clear sign of subduction, but we are actually more interested in the rocks that we see here in the foreground, because these are serpentinites. And serpentinites for a long time have been considered as green schistofacious rocks. They are schist and they're green, and they are associated often with green schist metabasalts. But here in Zermatt, we clearly see that these serpentinites are actually aquagite facies rocks. They are aquagite facies, and they underwent a first dehydration reaction, and that is the reaction of antigrite and brucite, the two minerals, serpentine and brucite, that we form on oceanic hydration. And we have here the formation of new metamorphic olivine, chloride, and the liberation of H2O. And these serpentines that are still left here, they still have a huge amount of water. These serpentinites at aquagite facies, they can hold still 10 to 12% of water. Also interesting is that they have a strongly preferred orientation. So that could be a reason for seismic anisotropy in subduction zones. And we have a development, we can have a development of a serpentinite channel, meaning that this would be a means of decoupling actually the slab from the mantle wedge, because we have a lubricant in between. Extremely important for seismicity and interpretation of geophysical data. Now, let's move a step further and see what happens when these serpentinites break down. Here, the best locality to study that is Sierra de Almirez in Spain, where the dehydration reaction can be observed in the field. So we see here on the right-hand side, we have still the serpentinites, very schistose rocks, then a transition zone, and then we have spinifex in Europe as well. But these are metamorphic spinifex. So this is not a komatiite. No, this is a dehydrated serpentinite. And because we liberate a large amount of fluid, 12% over a very small temperature interval, we have a fluid-dominated system where we can grow these large olivine and autopyroxene, and we form these spinifex textured rocks. So this means also the serpentine will break down. That will be the end of decoupling, and from this point on, we will have a coupling from the slab to the mantle wedge. So it's quite important to find out at what conditions this water is liberated. To do so, we can go and draw on experiments. So here is an example of experiment. Of two experiments, one at 640 degrees, where we still have here our serpentine mineral antigrade olivine here coexisting with talc. And then once we cross the antigrade out boundary, we have the autopyroxene, olivine, chloride, and a little bit of tremolite. And by doing many of these experiments, we can then constrain where the dehydration reaction is taking place. And we see that that is about here at 2 GPa at about 680 degrees. So that is would be in 70, 80 kilometers depth. The serpentine is stable up to 680 degrees. Now, what we can do more out of such experiments is also that we can investigate, we can use that to constrain the thermodynamic properties of antigrade. And here, Jose Alberto Padran-Navata has done that, has extracted thermodynamic properties, has reformulated an antigrade model, and that can then be used to calculate diagrams where we can see where the water is, how the water is liberated in a typical ultramafic rocks. You can see here the brucite and antigrade dehydration reaction will produce for this rock composition for spinel lertsolite host rock about 2.2 weight% of water. The antigrade out this one about 5 weight% of water, and then we have still a hydrosphase that is stable beyond the antigrade breakdown, and that is the chloride. So it is quite important here. Another field example. These are mafic dikes that have intruded into peridotite body. Then they have been serpentinized. The dikes have been transformed to rhodingites and then to meta-rhodingites. And here then we go and form garnet peridotites. And these are not garnet peridotites like in the xenoliths that come up in the kimberlites. No, these are metamorphic garnet peridotites. They derive from the dehydration of chloride, in this case, the reaction of chloride with clinopyroxene that forms olivine, garnet, and water. And after this, we see that there is no hydrosphase left. From the field, this is in a range, occurs in a range of 750 to 780 degrees. And let's check again with some experiments how we can constrain this chloride stability. So here, some technical details. That was a PhD thesis by Shane Lakey. That is a large amount. There are 53 piston cylinder experiments, every single experiment at least a week long, in order to constrain the different stability, the maximum stability of chloride in peridotite systems. We will have a look here at what happens at 3 GPa corresponding to these critical depths of about 100 kilometers. And what we can see is that we have 3 main reactions where chloride is reacting with other phases. The first one is that we have clinopyroxene reacting with chloride to form garnet, olivine, and garnet. Then when clinopyroxene is exhausted, we have a second one that is autopyroxene plus chloride going to olivine and garnet. And the final breakdown reaction is they are really in chloride-rich rocks, occurs between 840 and 860 degrees and forms olivine, garnet, and spinel. So from that, then we can construct a phase diagram that is shown here, a pressure temperature phase diagram, where we have the breakdown of antigride, as we have seen before, and then these 3 chloride dehydration reactions. They occur over a temperature interval of about 100 to 150 degrees and are significantly higher than the antigride stability. In previous experiments, these chloride reactions had a strong backbend, but in our experiments, we haven't seen that. And now, just to come towards the end of my talk, is we will have a quick look on how this impacts on the mass transfer from the slab to the mantle wedge. So what we do is the same diagram, but now we have here overlaying typical subduction geotherms. These are actually estimates on where the slab fluids have been extracted from the mantle wedge. And what we see is that they coincide quite nicely with the chloride dehydration reaction. And so what we think is that this chloride dehydration has been overlooked or has not been considered enough in order to form that this occurs at the condition that are very important to extract the material from the slab, then interact with the mantle wedge, and then produce the calc-alkaline magmas. And if you overlay on top of that, that is the wet peelite solidus, then we can see that for many subduction zones in this region here is when we have this water liberated from the ultramafic rocks, they will interact with the overlying sediments. They will melt the sediments, and then a slab melt will be a transport of water and trace elements and major elements from the slab to the mantle wedge. And so we can summarize this now in a diagram like we see here, that the first dehydration of brucite and antigerite will produce aqueous fluids at temperatures less than 650 degrees. This will be a low element mobility. Then we have the antigerite dehydration reaction. We have temperatures of around 700 degrees. We have an elevated mobility of elements, and very important, at temperatures higher than 750 degrees, between 750 and 840 degrees, we have the chloride dehydration in the slab, and we have melting of the slab and the extraction of elements. And this brings me, the serpentinites and the dehydration that we see, we can have partial melting of sediments that then will metasomatize the mantle wedge. We have the wet melting of the mantle, differentiation of magmas that ultimately lead to the granites. And this is the main way of how we form crust today. So it's this cycling of water uptake, water release. I have it here. So yeah, it's water uptake, water release, forming wet mafic magmas that ultimately differentiate into granitic bodies. And now we want to have a look how this situation could be in the Archean, and we swap over to René that will talk about the water cycle and crust formation in the Archean. Thank you for your attention.
Okay. Thank you, Jörg, for the really good introduction. As he said, now I'll be going back in time a bit to the Archean to look at sort of the relationship between komatiites, which I'm sure a few of you know a lot about, and TTGs, which I'm sure a few of you also know a lot about in the Archean. So just to sort of remind everybody, this is a kind of general timescale of Earth's history through time, going back from the Hadean all the way to present. And something I think is quite interesting about this figure is that each of these black sort of arrows suggest the time in the literature for when plate tectonics started on Earth, based on various amounts of evidence. Take what you will from that. But what's really interesting is that a lot of these black arrows seem to really be pointing into in the Archean. So the Archean is obviously quite an interesting time. We think there was some beginning of plate tectonics, whether that's as we know it today or as we maybe don't know it. We're unsure, but I think this is quite interesting. So as Jörg has showed you a lot of diagrams, this is just the same diagram of a modern day subduction zone where, as Jörg explained really nicely, the continental crust is formed in the overlying plate. And that is very much controlled by antigerite out and chlorite out dehydration reactions in the ultramafic material going in the downgoing slab. And this creates continental crust that is roughly diuretic to andesitic in composition on average. But if we go back to this time frame in the Archean, it was a little bit different, as we know. So some questions which people have raised, and I'm not going to pretend to answer these questions today, or all of them, but what was the continental crust made of in the Archean, and how did we make it? And what I think is the most interesting thing is, what was the role of water in the solid earth in this time, and how was it transported in the solid earth? So a lot of you probably know this map, of course. It's the Barberton area. This is the Barberton Greenstone Belt. Jörg and I just spent with Robert a couple of days down here last week. Beautiful area. And of course, as you probably all know, these cratons are very much dominated by plutons, these big TTG plutons. So a lot of people have sort of said that this is probably on average what the continental crust was made of in the Archean. It's buoyant, it's voluminous, and it's felsic. So some people have estimated that these TTGs make up around 80 volume% of the surviving Archean crust. And of course, as you know, we have the greenstone belts wedged in usually between these plutons. So a big debate for the past 40 or 50 years has been, how are these TTGs actually made? There's a lot of answers. It's a very complicated situation, but in general, we can say that TTGs were formed from the wet, so water present melting of basalts at quite low temperatures, as low as 750 degrees to 950 degrees, with the exception of some high temperature tonalites. And this has sort of come together over decades of research, including lots of field relationships, experiments, and thermodynamic modeling. And because we know TTGs aren't just made by one rock type, of course, we have differences in source chemistry, melting depth and temperature, and then igneous processes such as fractional crystallization and magma mixing, which can cause the wide array of TTG compositions that we see today. So they're quite varied in trace element and also major element composition. So what is sort of the evidence of this? So there's been some really nice experimental work. This is just an example of melting to form a TTG in experiments. Something that I think is really interesting is this paper from 2009, which looked at titanium saturation temperatures. So looking at titanium in the bulk rock of these TTGs. And that's what all of these gray dots are essentially here. And what they found from some experimental evidence was that titanium concentration in the produced TTG, is roughly sort of correlated with temperature and a little bit with pressure. That's what this diagram down the bottom here is showing. So these gray dots are examples from the literature, so real measured TTG compositions. And if you plot them on this diagram, which is showing titanium oxide and weight percent versus a sort of proxy for iron and magnesium content, you can see that most of the TTGs they have in this study fall at quite low temperatures of 750 to 950 degrees at pressures of less than 2.5 GPa, which is quite high pressure. So it seems that a lot of these TTGs definitely formed at lowish temperatures, and they definitely seem to have formed in free water or water saturated conditions, or water has certainly played an important role to make such voluminous felsic melts from basaltic material. A good question a lot of people say is, okay, well, we're melting basalts, and these basalts were probably hydrated, right? They were probably amphibolites by the time they went down to high enough temperature to melt, partially melt to form TTGs. And this is a really good point, because these amphibolites themselves can contain some water held in amphibole. But there's been a lot of work showing that the basalts themselves cannot form, or don't contain rather, the free water that we need to make these relatively water saturated melts. And this is just an example of a phase equilibrium diagram, which is at 9 kilobars. And what we have here is temperature on the y-axis and bulk water content on the x-axis. And the important thing to note is that an amphibolite, so a basaltic amphibolite, has maybe around 1 weight percent water in it. And at these low temperatures, so less than 900 degrees, we actually create almost no melt. If we go higher temperature or maybe slightly higher water content, we create a little bit of melt. This is the solidus, the red dashed line. but we certainly do not make huge TTG plutons where maybe we have 5 or less weight percent melt or more percent melt. So I think that this is a pretty good piece of evidence that the basalts themselves, they probably undergo some amphibole dehydration melting, but they're not liberating free water in large volumes that can help create the TTGs. So if we go back to the Archean, take this diagram with like a kilogram of salt. This is just the possible sort of tectonic scenarios we can make TTGs in, taken from all people in the literature. You know, you have subduction, maybe some hot underthrusting, you have interactions with flumes, you have oceanic plateaus, whatever was going on, that's all fine. I can't try and answer that. But the question really is, what is the source of free water for wet basalt melting? And I think you guys can sort of see where this is going, thanks to Jörg. And we think it's possible it's the komatiites. So the komatiites in greenstone belts are highly serpentinized, and many were erupted underwater. These are some pillared basaltic komatiites from the Pilbara Craton, but we saw a few in the Barberton last week as well. So they're maybe erupted on the ocean floor, they're extensively hydrated, and these beautiful spinifex textures are replaced by very, very hydrous serpentine and fluorite minerals. So they're not the most abundant rock type, this is true, but just in case you haven't seen what a greenstone belt looks like, sometimes, so this is an example, of course, from the Barberton greenstone belt, where you can have fairly thick sessions, kilometers thick, not purely komatiite, but they have a lot of komatiites in them, they're quite komatiite dominated. And of course, these aren't just found in the Barberton greenstone belt, they're found all over. So these pink dots here are different komatiite locations, so individual geochemical analyses. You can see, of course, we find them in the Archean cratons, but we have quite a high density in the Superior Craton, also in, of course, the Cartwell Craton, in Western Australia, India. So they're definitely found kind of all over in greenstone belts from the Archean. And this map is actually a database. So a database which was assembled by Matt Gart from the University of Adelaide. And what I've done here is I've plotted all the individual komatiite and komatitic basalt analyses from this database to sort of show you that this is the general trend we see in komatiites from all over the world. So this database is awesome. I'll show you more data from it. It contains obviously the GPS localities, the major element composition, and the trace element composition where possible. But I will come back to this. So if we look at a thin section image, this is what they look like. You can see the beautiful relic spinifex textures here that were probably once olivine. They've now been replaced primarily by antigerite, the serpentine mineral, and fluorite, which both contain around 12% water, so extremely hydrated. They also contain some tremolite and amphibole, as well as magnetite, epidote, lots of other minerals. But the key thing to really know about this is that right now, all of the komatiites have been metamorphosed to green schist or amphibole facies. So this is probably maybe not their assemblages upon serpentinization when they were erupting on the seafloor, but we can definitely use it as a proxy for the amount of water they contained when that happened. So this is an example from Barberton, but if we look at different komatiites from around the globe, I'm lucky enough to have some samples from people. These are some examples from the Yilgarn Craton, which have relic olivine, but still these very chlorite, amphibole, and antigerite dominated assemblages. And this is an example from India and also an example from the Abitibi Belt in Canada. And they all seem to contain more or less the same mineral assemblages and similar abundances. So we can quantify that. So this is just 6 representative samples I chose from around the globe. And this is just the water content of the rock in weight percent on the y-axis. And you can see they contain around 3.5 all the way up to 8.5 weight percent water. So they're extremely juicy rocks. And this water budget is is quite usually controlled by chlorite content, usually for around 50 or a bit less % of the rock's water. And then a lot in serpentine minerals and a little bit in amphibole. So if we now go back to that big data set I showed you, and what we do is we take all of these 5,600 analyses and we take the XMG of all of the analyses and we work out the mean LOI. So we're using LOI as a proxy for water content, which is roughly correct. These rocks don't contain humic carbonates. So you can see basically that as you go from low XMG. So these are the more basaltic rocks. You have LOIs around 3 to 4 weight percent. And then as we increase up into the komatiites, we really strongly increase our LOI, so our water content, all the way up to almost 10 weight percent. So this is basically the entire globe averaged into one diagram, or what we have preserved on the entire globe. But it's I think it's fairly representative to show that the komatiites are much more hydrated than basalts or any other rocks from that time. So that's all good. I've proved to you, well, hopefully, that komatiites contain a lot of water. But as I said, they're all green schist amphibolite facies. So they still have their water in them. They haven't lost their water at some point in their metamorphic cycle, whatever happens to them. So to work out what would happen, we need to do phase equilibrium forward modeling. So this is just a PT model where you have pressure here on the y-axis, temperature on the x-axis, so pressure roughly equaling depth. And then these are all the mineral assemblages we find as we would progressively metamorphose one of these komatiite compositions. And these sort of rainbow colored lines here are essentially water release in weight percent. So say we cross, there's a cross section here, A to B. This is a average Archean thermal gradient. Again, take that with salt. That's just what we have from recorded metamorphic rocks. But basically, you can see that we step over antigerite breakdown at about 500 degrees. Then we undergo a sort of rapid succession of tremolite and chlorite breakdown. And chlorite is stable in this composition all the way up to 800 degrees, similar to what Jörg showed us in the modern day serpentinites. So if we plot that along this transect, so we look along this thermal gradient, and we have fluid release here in weight percent, or water release in weight percent, you can see that chlorite and tremolite breakdown at temperatures of over 700 degrees is very effective at producing free water. So around 5 or so weight percent free water. So if we put all of those sort of lines of evidence together, this is the same diagram. I just wanted to show it without all of the phase relations in the background, showing the water release. These pink dots are metamorphic rocks from the Archean. So this is from the Mike Brown and Tim Johnson database. So not directly related, but kind of useful to see what are the thermal conditions we're reaching in Archean metamorphic rocks. So if you were to take your komatiite and bury it, whatever way you're going to do that, what are the conditions you might expect? So I think that's what this metamorphic database tries to capture. So we can kind of pin it down and say this is sort of the region in PT space that we expect metamorphism to be happening in the Archean. And now we plot on top our wet basalt solidus. So this is for a tholidite basalt. And immediately you can see, this is from experimental evidence, immediately you can see that the majority of our water release from komatiite metamorphism is above the wet basalt solidus. And that's regardless of the PT or the thermal gradient you choose. And that's simply because all of those phase relations you saw, including the chlorite breakdown, the antigerite breakdown, are incredibly steep in PT space. So it doesn't really matter which way you cross them. If it's high pressure, low pressure, you're still going to cross them and release fluid once you're above the wet basalt solidus. This is sort of the TTG formation temperatures from these titanium saturation experiments, a little bit higher, but in the same ballpark. So basically what I'm saying is that if you're burying your komatiites, perhaps they interlayered with basalts, as we see in greenstone belts now, and you release water into these basalts, they will partially melt to form TTG compositions. So you're under thrusting komatiite material, like you might in a subduction zone setting, you can dewater those komatiites and pump water up into any overlying basaltic crust and melt them again to form TTGs. So in this way, maybe these Archean komatiites, like this example here, are quite similar to modern day serpentinites, like Jörg showed us. This is an example from the Mid-Atlantic Ridge. They're incredibly different looking rocks because they formed in completely different scenarios, but they probably played a really similar role in water cycling and continental cross formation throughout Earth's history. So just to bring that all back, if we look at maybe what happened in the Archean, you'd be looking at antigerite out in the upper crust and tremolite and chlorite out in the lower crust, perhaps as sources of water to melt basalts in the Archean. And thank you.
Okay, thank you very much, Jörg and Renee, for these Schulich's very interesting presentations, nicely illustrated. And I'm sure there are many questions from the audience. Lou?
I have one question for Renee and one for Jörg. It's so that if you're solidus, if your salt solidus is water saturated, then you're never going to be able to place those melts to shallower depth because they're going to freeze, they're going to solidify. So I think your melting cannot be water saturated.
So I'm not sure I completely understand the comment.
Show me your last PT diagram.
This one.
Okay, you've got that red dashed line.
Mhm.
Suppose you form a melt on that line.
Mhm.
By whatever process you like, increase the temperature or whatever. Then if you try to reduce the pressure on that melt that sits on that line, it's going into the field of solid.
I'm with you.
And the melt will stay at depth. You can melt it, but you can't get it up. Sorry to use that.
Okay, so that's a very good point. And that is, of course, if you melt here at the solidus, because then you cannot. But the interesting thing is that we look at the two rock system, an ultramafic rock that by itself will never melt, and the mafic rock that when the water comes in will melt. And the water comes in here. So it won't melt here because the ultramafic rock has not liberated the water yet. So the melting is here. And from here you can bring it up.
Show me the solidus on it for your pointers.
That's the solidus here.
Where?
The wet basalt solidus is here.
How melt occurs? Oh, I see.
It will go here and we'll have an adiabatic uprise.
And you're superheating the whole system.
No, you don't.
Superheat the system. You're
Yeah, no, it is that you liberate the water. Yeah, you superheat because it's a two rock system. You liberate the water at conditions that are already well above the wet solidus of the mafic rock. The ultramafic rock will liberate here at these temperatures at 750, 800 degrees, and then you'll be able to bring them up to about here to upper crustal levels. That's why you see the plutons.
There has to be a solidus.
Yeah.
Yeah.
Yeah, no, it's that. It's that. Goes here and goes here. You might not see it. It goes
Hang
here,
on.
here, here. It was first indicated.
Oh no, I don't have it. Oh, good. Sorry, I was just
It's my solidus.
getting rid of it.
Yeah, I see that.
Yeah.
Yeah, but slope is this way. If you're sitting on that curve, it can't go up.
No, but we're not sitting on the curve. We're sitting we're starting here.
So where is the melting reaction? Where your pointer is?
That is the,
Oh, so the melting reaction is like that.
yeah,
But then it's okay.
okay.
If those are all solids.
No, they're not. They are the water liberation. That's the water liberation in that.
That's the solids. Before I can judge whether or not you're able to bring this melt up. That's the solid.
Yeah, so that's the solidus is the basalt solidus that is relevant.
Oh, that doesn't help you to get them up.
It is that the melting is when you add the water from the ultramafic rock to the thing.
If the solidus has that slope, no,
It's the dehydration that has this curve.
dwell on this.
Yeah.
That's me.
Okay, I think Ron has got another question.
I have a question for him.
Yeah, okay.
Can I do that?
Yeah, sure.
Okay. Understood your talk very well presented. Well, thank you. Students will greatly benefit from this. I'm just wondering if any of your work says anything about how you get the slab back up to the surface. You know, like to expose blue schists and eclogites, as you see all over the place.
Yeah,
How do you get that stuff back up?
yeah. So great question. So this is again what I explained to my students that that's the serpentinite taxi. So the thing is that also for this process, the serpentinites play a key role because the serpentinites have a density of 2.7. And so what we have seen is that while the eclogites, the mafic rocks are already eclogites at 550, 600 degrees, 20 kilobars, the ultramafic rocks are still serpentinites. And so if you have a body of eclogite enclosed by serpentinites, the bulk buoyancy of that package of rock is still less than the surrounding mantle wedge and you can have a buoyancy exhumed because you have these buoyant serpentinite bodies. And the interesting thing is that you won't find an oceanic eclogite that comes from PT conditions beyond serpentine dehydration.
So you still would expect to see the eclogite surrounded by serpentinite on the surface.
Yeah, that's what it is here in the
I've
summer.
never seen that. I've seen lots of eclogite surrounded by blue schist, but never ever surrounded by serpentinite. But maybe I just have to look at it more. I don't know.
Go for melanges.
What?
Yeah.
Melanges?
Melange, tectonic
You go to
melange.
Corsica, you go to.
Ah, Corsica, plenty of
Plenty of
serpentinites.
eclogites, but they're in pillows. They're still in pillows.
Yeah.
They are not surrounded by serpentine.
Oh, well, there's lots of serpentinites as well in Corsica.
Yeah, perhaps we can move on with Grant. Grant has a question and then
Thank you both for a really interesting talk. My question kind of follows on from Lou's question. I have two parts to this question. The first part is, there's obviously lots of debate around the style of recycling in the Archean, right? Was it, drips going down into the mantle or subduction, as we know today, at a steeper angle? Does the style of recycling influence anything in your model? Is the first part of the question.
I would argue probably not. I'm thinking. I would argue in general probably not, and that's simply because these reactions are so steep. So if you're doing, doesn't really matter on the PT path your rocks undergo. So obviously, if you're dripping, it'll be a very warm to high pressure. If you're subducting, it'll be cooler to high pressure. But you still basically cross the wet basalt solidus before you're dehydrating the majority of your rock. So, but it might preserve it might reflect what's preserved. Meeting.
I might just add one. So the thing is, what will be influenced? Let's see if we can. What will be influenced is the melt productivity. If you have an underthrusting event, then you go from cold temperatures to hotter temperatures. So you can actually, by this mechanism, if you have a given amount of water, as you move upwards, you have the possibility to increase the melt volume. So in order to produce very voluminous bodies of TTG, an underthrusting is favorable in terms of melt production.
Okay. And then the second part that follows on from that is basically asking in the models of the transition from Archean to Proterozoic magmatism, people like Sisova and Mike Brown think that you change recycling style again. Do you think and they propose a much hotter subducting environment, do you think that would shut off the water supply to the mantle wedge in the Proterozoic? And is that why we see less hydrous magmatism in the Proterozoic?
That's a good question.
Yeah, so that's a very good question. For sure, the hotter the subduction is, the earlier you dehydrate, and the less water so for the mantle wedge melting, that will have an influence. What we are now researching on is how much water can actually then be retained in the nominally anhydrous minerals. So that is another completely, that would be another talk just on the nominally anhydrous minerals, because these are then the minerals that will transport the water to the deep mantle. And normally pressure helps as well to retain water in these nominally anhydrous minerals. So the colder the subduction, the more chance there will be to retain water in the nominally anhydrous minerals to bring them then to the lower mantle.
From the room? Just check and see if anyone online has questions. If there are any questions online, simply raise your hand and we can get to the questions online, or we can check them out in the chat. But let's start with a question from Sue while I look at these questions.
So I'm a geophysicist and because it's a geology talk. And so, but I'm interested in this magnetite that keeps coming and going. And where you might think it gets stuck in the crust or the mantle, or is it always resorbed? Because we do see very large scale deep magnetic signatures, and they're always debated. And so I'm wondering about how we can use the geophysics. I mean, we have some of our own ideas about how you can use the geophysics to actually mark out some of these subduction zones based on some of these transitions. So I just wanted to question that.
So the question was where the magnetite will be formed.
Or accumulated, or what happens to it?
But what happens?
Magnetic signatures in many of these, what we think are collisions.
Okay, so what we see when we looked at in recent studies, we have looked on the evolution of magnetite on ongoing subduction. And what we can see is that we see them to about 100 kilometers depth for sure. Now, these are coming from serpentinites that are formed in slow spreading ridges, where we have exhumation of mantle to the seafloor. And there where we have extensive serpentinization, we have a lot of magnetite forming in the first kilometer of interaction of seawater with the mantle, exhumed mantle rocks. So these ones we know that there's magnetite, and that will be stable to the ones for the normal size, for the morbs, where the mantle is at 7 kilometers depth. We actually don't know how much magnetite, if at all, that we form, because there's very little evidence. So the Oman of your light is still unclear how much how much of the magnetite is actually to seafloor alteration or other types of alteration. And in the bending, we have no idea at all. So I can say for the slow spreading ridges, we have good ideas that we have extensive magnetite formation. For fast spreading ridges, we don't really know to the bending now.
Okay, and then I think we have a question from Nick Arndt, who's online. Nick, go for it. We should be able to hear you through the projector.
Hear me and see me? I've done, yeah. First, I agree with Jörg. In order for there to be much granitoid produced by dehydration, there has to be underthrusting in order that water moves from hot rocks from colder rocks that are dehydrating upwards into hotter rocks, as in underthrusting, as in subduction. In a vertically descending drip, the water essentially moves from hotter rocks into colder rocks. It doesn't do much of anything. But my main question is addressed to René, and I wonder whether you've not underestimated the water content of Archean metabasalts. Now, it's true that in an amphibolite with just amphibole and plagioclase, there will only be about 1%. But most Archean rocks, in most Archean greenstone belts, the metamorphic rate is green schist, more green schist plus or minus. And if you look at the contents, the water contents, the LOI of Archean basalts from Barberton or Abitibi or Zimbabwe or elsewhere, they're around 3 to 4% water. And basalt is about 9 times more abundant than komatiite. Very few greenstone belts contain more than about 10% komatiite. So I'm just wondering if you're overemphasizing a little the possible role of komatiite as a source of water.
Yeah, fair enough. Thanks for the comment. You're definitely right. Some of these more magnesian basalts, like the komatitic basalts, can have a bit of chlorite, so they can also dehydrate at high temperatures. I guess in the database, so that's the main sort of data I had to look at. There was a lot of analyses, but you really see that big dichotomy, that big shift that I showed in the XMG diagram when you go over the border, basically, so XMG over 0.75 or so. So you're right, they probably do also play a role. It would be nice to have actually some really good estimates of how much of everything is in the greenstone belts. That's kind of difficult to come across, like how much komatiite versus how much.
Well, no, that's not really. These estimates are present in a paper. For example, Lou, in the book you co-edited, there are estimates of the proportions of different types of rocks, and I don't think there's much discussion about the proportion. We can talk about the exact numbers, but most people would say that metatholite, not the komatitic basalt, but the metatholite, is by far the most abundant rock in Archean greenstone belts. And they contain typically 3 to 4% water because they're in facies.
Yeah, there's a bit, I see in your comment as well, you mentioned the sediments, and it's a good point that they contain water, but the problem is they're not releasing it. They're not undergoing dehydration reactions at the correct temperatures. So the tholeiitic basalts are undergoing amphibole dehydration melting, but they're not pumping free fluid into themselves. Same with the sediments. At those temperatures, the sediments are not dehydrating to release water into the basalts, they're partially melting themselves. So what you really need to find is a rock that's not undergoing partial melting and can liberate free fluid.
Well, no, maybe you can comment. I think there's a long discussion, and it's true that the dehydration reactions that release most water happen at relatively shallow depths. But then there's the question of whether corner flow can within the mantle wedge can transport this hydrated peridotite to deeper levels where melting can take place. Is that still the sort of thing idea that's being thought about?
Can I just give an addition to the
Sure.
To the question about the water contents in basalts? It's true that if you do a loss on ignition on the basalts as they are sampled, but that is green schistous conditions. So before they hit the solidus, they will have metamorphic transitions. They will lose a lot of water, and the rock type that is just there before we would overstep the solidus is an amphibolite, is amphibole plagioclase, plus minus garnet, and that has only 1 to maximum 1.5% of water. So the mafic rocks, the thing with the mafic rocks is that all these dehydration reactions are also dependent on the XMG of the rock. And the more iron we have, the earlier the dehydration reactions take place. And therefore, and that is one of the reasons why when we come up to the region where we can melt, the mafic rocks are much drier than the ultramafic rocks. And that's why we think, although the ultramafic lavas are not as abundant as the others, in terms of water budget, they are quite significant.
But do you think then that the melting that takes place to produce the parental magmas of granitoids happens within the slab or within the mantle wedge?
For the Archean case or for the...
Or for both? Both, yeah, both cases.
Want to get back?
Yeah.
Give me a second. I'll take you back. Good.
I might just go to the... Oh, no, is it mine?
I can get that for you.
Okay.
It was a good discussion.
Yeah,
We
no,
should
I'm
continue.
enjoying that. Yeah, we have time.
We have time.
Yeah, it's Saturday.
Listen,
Maybe we just go on to... No,
you can go for it. Yeah.
Yeah, so if you look at the current day, so that's my view on the most important way of producing the granitoids in the current day is that we have either antichorite dehydration in the deeper parts of the slab or chloride dehydration close to the top of the slab, and that will induce sediment melting in the sediments that are subducted as well. And that will give the characteristic trace element signatures that we then see as subduction component in arc lavas. So in order to produce the subduction component, we have to have, for the barium, the thorium, that has to come from the sediments, and melting is the most, melting of these sediments is the most efficient way how we transport this slab component from the slab to the locus of partial melting. But then the basalts, of course, are produced by this slab component. The water will flux the wet melting, and that will then produce these basalts that will have the majority is melting of peridotite that produces basalts, and have this distinct addition of the sediment melts that impact on the trace element signatures of the primitive arc lavas, and that is then transported through the differentiation into the granites that form the continental crust. So that would be my take for the current way of producing crust. Now, in the Archean, I think there is an important, is different that we can have in this underthrusting. It's not necessary that we go through a melting of the mantle. So we could have a dehydration in a cold underthrusting, dehydration and then migrating to hotter paths, and by that having this increase of amount of melt in also in a flux melting where, as we suggested, some of the water will come from the hydrated komatiites and melt the surrounding basalts, wet basalts, and then melt volume will increase as these, as long as the temperature increases on the rise up. If there are the drips, and if we have then here also melting of the mantle wedge, and then production of basalts, there are basalts, there might be hydrous basalts, there might be basalts with a kind of a slab signature, but how much in volume that this process might contribute to crust formation, I don't know.
Okay, great. I think we'll just take one last question from the chat, if we may. And I'll Josh 2 questions. So let's take Josh's last question. TTGs are seen as large plutons, so surely loss of water from subduction, which frequently appears channelized or would form relatively small melts, cannot form these huge homogeneous plutons in big diaperic blobs.
I mean, it's a good point. So I guess the problem is what we're missing the connection between the dehydration of the rocks and the product. So like now you can go find like water escape channels, and you can see all the kind of processes that happen in the mantle wedge now. But in the Archean, we don't really have that information. So you're kind of asking the question is, how do you make a pluton? Which is a difficult one. You go.
Yeah. So it's a great question, and we would love to answer this, of course. The thing is, what we observe in the field, and also when we look at melt formation, is that in subsolidus conditions, of course, the fluids are channelized, but as soon as you hit the melting region, then it can actually disperse, and then it will go from a channelized flow to a mush of rocks with melt in between, and then this melt can segregate to form and to uprise. I agree, the volumes of the TTG is one of the most puzzling things. It's just huge, and to see how you can form these big plutons is difficult. But the only thing that we can say is, without having additional water, it's even more difficult than if we have additional water.
Okay, great. I think we'll leave it there. Clearly, this has stimulated some discussion. So thank you both. Fantastic. Thank you for visiting us. Thank you, Rob, for arranging this. And that was the last talk of the first semester. So thank you, everybody. And we'll see you again in semester 2, which is not that far away, in 1 month's time. Thank you, everyone.
Thank you very much.
We had a great audience. We didn't pull them in during a vacation. Such a big audience. Yeah.
We'll both be at Goldschmidt, yeah.
So Jürgen Rene, are you still online?
Yeah, we will be.
Yeah, I think you can still hear you.
Next week,
If there's something.